We're going to talk about derivatives and what does it mean to be a derivative in 3 dimensions or higher. Now remember, a derivative means an instantaneous rate of change. So an instantaneous rate of change, most people think of it as slope. Well, if I have a graph and I say, what's the instantaneous rate of change of y with respect to x? Yes, that's the slope of a tangent line. But if we're talking about motion in 3 dimensions and different things, no, there's no tangent lines associated with it. So if I want to do something 3-dimensional, I'm climbing a hill and I say, gee, what is the slope of the hill? Well, if I'm on a road and I have a road that's flat, the slope would be 0. If my road's going uphill, we call that the grade. That's what the slope of the road is. But it's the idea is being, I'm moving straight. I might be going uphill, but I'm still going straight. If I start turning, now I have 3-dimensional motion. So how do you describe slope? Since slope is the rate of change of y with respect to x in 2 dimensions. So if I'm in 3 dimensions, I have to kind of be careful how I define it. So what we actually do is we say, consider slicing an object. And we'll do a little bit of this. So, and let's suppose z is a function of x and y. And I have some surface, here's my surface. Here's z equals f of x, y. Now, at any point on my surface, I can talk about things like what's the slope. But since I can move in 360 degrees, slope actually has to be in a direction. Oh, so if I said, let me slice it along the x-axis. So kind of think of a slicing this way. Now what I've got is a rim. I've got an edge of my curve. And that edge is purely 2-dimensional. If I said, let's slice it this way, so maybe I'm going across here, so now I'm slicing it that way. So again, I get an edge or I get a rim. When I take a 3-dimensional object and I slice it parallel to any of the planes, what I'll get is an actual curve. I'll get a 2-dimensional curve because of my 3-dimensional slice. This is not a solid shape. So think of this, I like to use this analogy. I'm making my bed. So I'm taking the blankets on my big king size bed and I'm fluffing them up in the air so they can fall gently down. So as I'm fluffing my blanket's looking like this in 3D. Let's just freeze it right there. Now I have a 3-dimensional surface right in front of me. And if I said, what's the slope? Well, it depends. If I slice it this way, then I have the edge of my blanket. If I slice it horizontal, then I have the edge of my blanket. Every time I slice it, I have a 2-dimensional rendering. That's what the cross sections we talked about before are. But in this case, the only 2 slices I'm interested in are the ones with respect to x or with respect to y, because z is my dependent variable. Okay, so let's go back and remind ourselves, how do we do a derivative in Calc 1? So I want to remind you of the definition of the derivative in Calc 1, because this is what we tweak to do it in 3D. The definition of the derivative. So if I have y equal f of x, then we said that dy dx, which we also call f prime of x, depending, did I say y is my function or did I say f of x is my function, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And you're very familiar with this in Calc 1. You did this, you derived about half of your derivative formulas, x to a power, sine x, cos x, e to the x. We use this to derive most of our formulas early on. So if I said, I want to take the derivative of, keep it simple. Yeah, mute yourself, please. Guys, make sure you're muted. You're much louder than me. So if I wanted to do something like, let's say, the derivative of the square root function, okay, then we wrote it like this. And this is just a reminder. So f of x plus delta x minus f of x over delta x. Now, delta x is the problem child. Delta x is the thing that's going to 0. So delta x is the thing I would like to remove from the problem. So in order to do that, I kind of have to get the delta x out of that root. The easiest way, of course, was to multiply by the conjugate. Now I know this is legal because I'm multiplying essentially by 1. But when I do that, I create a situation where I may be able to cancel common factors. So let's keep going. So my numerator would be x plus delta x minus x. Okay, again, a minus b times a plus b is a squared minus b squared. And when you square a square root, well, that's what you get. All right, so x plus delta x plus delta root. There we go. Well, my x's are going to cancel. And so now I just have the limit as delta x goes to 0 of delta x over delta x times the other stuff. It's still an indeterminate form, but my problem child, which was the delta x, I can now cancel. I can now remove that from the problem, and I will have 1 over the square root of x plus delta x plus root x. Now I can let delta x go to 0, and we get 1 over 2 root x. Now we know we have a derivative formula for that, but this is how we derived it in the first place. We used the definition of the derivative, and you can always do this. It's just the algebra might be intense. So now how do we do this in 3D? This is the whole point. Well, we actually use the definition of the derivative in 3D as well, but we only move one variable at a time. So I'm going to walk you through that process. It's not difficult. It's very prescribed, but once we do it one time, I think we'll get the hang of it. You're not going to be doing this in general. I'm doing this to remind you, just as a review here. So now I first want to start off with the notation, because notation is everything in calculus. It doesn't matter what you say in calculus, it probably means something. So if you say something, but you meant something else, but the notation you use is interpreted the way it's supposed to be, it may not be the way you wanted it to be. That sounds crazy, but we all do this. So in Calc 1, I have y equals f of x, d dx is the differential operator. The differential operator. That's all it is. It's basically it's like a square root symbol. Okay, it requires an argument. And in Calc 1, this is probably the part of the course that takes the longest for people to get the hang of. You see, if I said to you square root of x, excuse me, not square root of x, sorry. If I said square root equals, or the natural log equals, or the limit as x goes to 5 equals, there's something wrong with these statements. They're all missing something. They're all missing an argument. The square root of what? The natural log of what? The limit of what? You actually have to have an argument. It doesn't make any sense because the root, the log, the limit, they're just operators. They operate on the argument. So I actually have to have an argument. D dx is exactly the same thing. It's like a function. It's an argument that, or excuse me, it's an operator that says d dx applied to whatever follows it. And that result will be a derivative. But d dx isn't equal to something any more than the empty square root symbol isn't equal to something. But Calc 1 students always take a while to get the hang of that because d dx looks a lot like dy dx. So if I apply d dx to both sides, then we say that d dx applied to y is dy dx. D dx applied to f of x is, and we say f prime of x. It doesn't matter which notation you're using. It only matters that you define your function with this symbol or with this symbol. You don't write f prime if you're using y, and you don't write dy dx if you're using f, because there's no guarantee that y is even in the problem. Yikes. So now that's easy enough. What about higher level derivatives? What if I want to take the derivative of y? Okay, that means I'm taking the derivative of dy dx. Well, the notation we've always used is we say d squared y dx squared. And now there seems to be a bit of redundancy there, and it's actually on purpose. This says take the second derivative of y, and then I put because dx is considered one symbol, I put the square here because we're saying both with respect to x. So I'm saying d dx twice. That's why I put the square on the d and I put the square on the dx. The dx is like a single symbol, almost like there's parentheses. But I don't put an exponent on the y. I'm doing d dx twice to y. Now, Calc students always ask, why do we need it in both places? Because I'm taking both derivatives with respect to x as if I could do something else. Yeah, in 3 dimensions, you can. So in other words, this notation will make a lot more sense in 3 dimensions than it did in 2. So higher derivatives, I just keep doing this. What do we do in this case? Well, when I do d dx of f prime of x, we know that's f double prime of x. Okay, piece of cake. Well, it turns out after a certain point, we change the way we write this. You see, and mute yourself, guys. Okay, I shouldn't hear any background. There's no reason to be unmuted at this, unless you have a question. So if I said I want to do the nth derivative, then we actually write dny dxn. But if n is bigger than 3, do you write f? I don't think you do that. That would be really hard to interpret. No, if n is bigger than 3, then that's how we write the nth derivative using that notation. This notation is actually easier than that notation, but that's what it means. Okay, that's how we did it in Calc 1. This is called, and this is very important, an ordinary derivative. An ordinary derivative. That doesn't mean, a run-of-the-mill derivative. It's just generic like all others. No. There's only 2 types of derivatives. There's ordinary, which is what we've done in the past, and there's what we're going to do today, which is called partial. Those are the only 2 ways you can differentiate: ordinary, partial. In Math 255, right? That's called differential equations. Actually, it's called ordinary differential equations. The upper division version of that class is called partial differential equations because it's a little bit more complicated. And so that's what we're going to learn today. So first thing is, before I even show you how to take a derivative, I want to show you how to write a derivative. Okay, d dx was the symbol we used to do an ordinary derivative. Okay, so now I have z is a function of x and y, and I want to differentiate. But do I want to differentiate with respect to x? Or do I want to differentiate with respect to y? Well, I can do both. Oh, so there is no more prime notation. You'll never use it again the rest of your life. There's no more f prime because it's ambiguous. But there is an analogous notation that we'll use. So I want to differentiate. I'll put diff with respect to x. First of all, the symbol looks like this. Curvy d's. Okay, ordinary vertical d's. And by the way, it does matter. There are folks who just write kind of ambiguous. They write kind of sloppy, and it's not really clear which. Nope, straight up and down d's means ordinary derivative. Another way of looking at this symbol means there is exactly one independent variable, and that independent variable is x. That's what it means. You can have infinitely many dependent variables. I can have 10 different things all be functions of x. That's okay. Right? When we did our vector value functions, R of t, didn't we have x of t, y of t, and z of t? X, y, and z were dependent variables, but they were all functions of the same independent variable t. That's totally okay. This says there's exactly one independent variable, it's x. This symbol means there's more than one independent variable. It doesn't say how many, it just says there's more than one. So I want to differentiate with respect to x. So this means it's going to be a partial derivative. So this is the notation for partial derivatives. I'm going to apply this to z, and we write it like this: partial z with respect to x. If I apply it to f, I can write it as the partial of f with respect to x. That's totally okay. But my preferred way of doing this, that's the equivalent of the f prime notation, is we actually write f with a subscript of x. You'll like this notation for the same reason as previous notations. It's just less to write. So if I'm using function notation, these say the exact same thing, but there's no prime. There is no prime when you have multiple independent variables. That symbol's never used again, unfortunately. Sorry. So now that's with respect to x. What if I want to do it with respect to y? Oops. Make that a y, sorry. Well, that's kind of the oh duh. That would be partial of z with respect to y. Oh, that was easy enough. What about higher derivatives? What if I want a second or a third derivative? Okay, now you're going to see something about notation. All right. If I said I want to take the partial with respect to x of the partial with respect to x of, I'll leave it as, sorry, I'll leave it as a z, easy notation. And we write, okay, when you take a derivative in Calc 1, you have a new function. And then I can take the derivative of that function, and I have a new function, and I can do this indefinitely. So I've just taken a derivative with respect to x. And what I want to do is now take the derivative with respect to y of my derivative with respect to x. Ooh. So what does that look like? That looks like that. I took two derivatives, one with respect to x, one with respect to y. I could take 5 derivatives and 3 of them with respect to x and 2 of them with respect to y. I could do them all with respect to x. I could do them all with respect to y. This says how many derivatives I took, and then think of each of these first power if you want. And then the denominator says how many did I do with respect to each variable. That's why we use that notation. So in Calc 1, when I do that second derivative and I put the 2 on top and bottom, it always seemed redundant that I put it twice. Now you realize I put it twice because when you have multiple variables, you use the same notation. That's how many derivatives? That's with respect to each variable. Okay, so that's really nice. Now, what about the F notation? Well, it turns out if I take the partial with respect to y of, I've already done the partial with respect to x. Okay. Now, some textbooks will say this is fxy. Some will say it's fyx. It's not always exactly clear. Okay. It's going to turn out, we're going to show it doesn't matter. Okay. We're going to prove it doesn't actually matter. So either one of these would be okay. All right. Now let's actually do a derivative so we can see how this works. And I'll take something that's not horrifically big, but I don't have a lot of space. So unfortunately, I'm going to have to do some erasing at some point. Let's start with a really simple function. Let's say z is 4x squared y cubed. Okay. I want to find the partial of z with respect to x. I'm not getting cut off there. And the partial of z with respect to y. I want to find these two derivatives. And what we're going to do is use the definition of the derivative, but I'm going to show you how it looks. So the partial of z with respect to x is the limit as delta x goes to 0, but of what? Now, I'm going to say it generically, and this will make perfect sense. If z equals f of xy, then the partial of z with respect to x, which of course we just write that way, is the limit as delta x goes to 0. That part looks just like what we did in Calc 1, but what goes here? I replace x with x plus delta x. And I don't touch the y. So the partial of z with respect to y, or fy, I'm going to take the limit as delta y goes to 0 of f of x comma y plus delta y minus f of xy. So the definition of the derivative in 3 dimensions looks a lot like the definition of the derivative in 2, but I can only take one limit at a time. Remember, x and y are independent variables, so I'm not taking the limit simultaneously, for all of these. So this is the partial with respect to x, this is the partial with respect to y. And you notice this is what I do. And that should make perfect sense, because remember I said you're doing a slice. So if I slice it in the y direction and keep y fixed, now I'm basically looking at the xz plane. If I do it the other way, I'm looking at the yz plane when I make my slice. So there is no other variable moving at that time. So this this will be, now I want replace x with x plus delta x. Oops, the limit of 4x plus delta x quantity squared y cubed minus 4x squared y cubed over delta x. Okay? That's what I want to do. Now I need to expand that, which is just algebra. So off to the side, if you need to, I'm going to square the x plus delta x term. And when I do that, I'm going to have x squared. So this will be, I'll just do this off to the side. I don't want to lose anybody. When I square that, x squared plus 2x delta x plus the square of delta x. Now I'm going to multiply that by 4 and y cubed. Okay, so that's going to be 4x squared y cubed plus 8, where's it? X delta x y cubed plus 4 times the square of delta x y cubed. Okay, quick check there. Did I do that correctly? 4y cubed times this, 4y cubed times this, 4y cubed times this, right? Minus 4x squared y cubed all over delta x. Now in Calc 1, anytime we had an algebraic statement like this, I mean, I'm not talking sines and cosines and logs, but you actually something that was just purely polynomial-ish, you notice that always every term without a delta x in it canceled in the first step. And in fact, if they didn't, you know something went horribly wrong. Every term that's left will have a delta x in it, and that's a good thing, because then I can factor and cancel with the bottom. So what's left on top is 8x delta x y cubed plus 4 times the square of delta x y cubed all over delta x. Now I can factor the delta x out. That will take one step. Then I can cancel the delta x's out. That will take one step. I'm lazier than that. I don't ever actually factor and cancel. I say factor and cancel for everyone else, but that's not what I do. I'm lazier than that. See, whenever you have a quotient, factoring and canceling is what you're supposed to do to simplify. But if you're fast, you can do that in 2 steps. You can't factor and cancel one. They're completely unrelated mathematical steps. If I'm factoring and canceling the delta x, there's an easier way. Just do that. Yeah, I figured that out as a kid. Don't factor and cancel. Just multiply by the reciprocal of what you were going to factor out and cancel in the first place. Then the next thing you write is the finished algebraic version. You see, I'm going to have a 1 on the bottom. I'm not going to bother writing the 1 on the bottom. But on top, what do I have? I'll have 8xy cubed plus 4 delta x y cubed. All over 1, if you like. Now, when I take the limit as delta x goes to 0, this is no longer an indeterminate form because I no longer have a denominator. That term's going to 0. I'm going to end up with just that. Wonderful. So what I'm going to do, I'm going to write that up here because I need to erase the entire board because I will not have room otherwise, because I got to do this again. So this is 8xy cubed. Okay, great. And then in a moment, I'll do the other one. So, okay, so that was the easier of the two. The next one, we got a cube. It's going to be a little bit messier, but we can do it. We're tough. We can handle it. I might have to write a little bit smaller. And all right. So now let's do the derivative with respect to y. So now the partial of z with respect to y is the limit as delta y goes to 0. Now I'm going to replace y with y plus delta y. No delta x's in this one. So I'm going to have 4x squared y plus delta y quantity cubed minus 4x squared y cubed all over delta y. Now, the cube might be a bit of a problem if you don't know how to do that off the top of your head. So let's do that off to the side. Can't afford an error. So if I have y plus delta y cubed, that'll be y cubed plus 3y squared delta y plus 3y times the square of delta y plus the cube of delta y. I'm just cubing. That's the cubic expansion, right? Binomial, that kind of stuff. So I'm going to multiply this by 4x squared. So 4x squared y cubed plus 12 x squared y squared delta y plus 12 x squared y square delta y plus 4x squared cube of delta y minus, can you get in there, 4x squared y cubed. Okay, barely got it in. Should have wrote it a little smaller. All right, does anything cancel? Well, just like before, that and that. They are the only terms that do not have a delta y in them. And they're the only terms that cancel. That's a good thing. That's a really good thing. So I'm left with 12x squared y squared delta y plus 12x squared y times the square of delta y plus 4x squared times the cube of delta y all over delta y. And like before, let's just multiply top and bottom by 1 over delta y. That saves me from having to do the entire factor and cancel step. When I do that, I'm left with, okay, what do I have here? I have 12x squared y squared.
That's supposed to be a y cubed, isn't it?
On which one? This one?
Yeah. Oh, never mind. I'm sorry.
Remember, we already canceled those guys. Yeah. Remember, we multiplied 4x squared by the cube, so that's how the remaining terms. So notice this is y cubed, y squared, y to the first. They are descending at that point. So what's left? And then 12x squared y delta y, and then 4x squared times the square of delta y, because I canceled. I can easily evaluate this guy. That's going to 0, that's going to 0, and I'm left with 12x squared y squared. All right, let's put that result on top. Oops, 12x squared y squared. All right, man, that was a lot of work. Do I have to do this every time? No, I'm probably never going to do it again, because I think we can see exactly what's going on here. When I'm taking a partial derivative, that means I'm holding one variable fixed. Quite literally, it means when I'm taking the derivative with respect to x, I am quite literally treating y as if it's a constant, as if I'm treating y like it's a coefficient in the statement. When I did the derivative with respect to y, x was just acting like a coefficient. That's the part that was changing. Now, if that's the way we define the derivative in 3D, notice my final results. Does anybody see it? Is it jumping off the page to anybody? When I took the derivative with respect to x, 4x squared. What's the derivative of 4x squared with respect to x? 8x. Look at my answer. When I took the derivative with respect to y, see, that'd be, forget the extra one, that'd be 12y squared. So when you're taking a partial derivative, quite simply, you keep the other variable constant. You treat it as a constant, and you differentiate the variable you're looking at, which means that derivatives in 3D are just like derivatives in 2D. I have all the same rules, but I'm only looking at one variable at a time. So you never have to do the limit. I did that to show you. I could have told you, but I showed you. So the derivative with respect to x, oh my gosh, I'm just going to go 8x y cubed. The derivative with respect to y, okay, 3y squared times x squared. That's it. So let's do a whole bunch of examples until we feel like we got this. Of all the things we do this semester, most folks get this the fastest. All right, so let's do an example of this. Let's suppose we're doing, let's say, f of xy is 6xy squared minus sine x plus 3 cosine xy. All right. I would like to find fx and fy. Okay, let's find fx and fy. Well, let's see. To find fx, that's the partial with respect to x. I'm using this notation just so you get used to seeing it. I have three terms connected by sums. That's not a big product, so I have three completely separate statements here. The derivative of the first with respect to x, that means I'm treating y squared as if it's part of the coefficient. In fact, it might be safer to look at this as 6y squared times x. So I have constant times x. What's its derivative? Just the constant. Okay. In the next one, I only have a function of x. So the derivative of sine x is just cos x. Now in the last one, I have, you said, like, I have cosine of xy. In Calc 1, we'd need to use product rule on that. Yeah, because in Calc 1, y was a function of x. Y is not a function of x. X and y are completely independent variables. That means one of them will be treated as a constant when I differentiate with respect to the other. I want the derivative with respect to x. That means this y is treated as a constant. So this would be minus 3 sine of xy times the derivative of xy. But the derivative of xy with respect to x would just be y. Y is like the coefficient. Now, that y I should write right here because it reads a little bit better, but that was basically my chain rule factor. Now, what about the derivative with respect to y? Now I treat the 6x as a coefficient. So this would be 12xy. What do you think the derivative of sine x would be if I'm differentiating with respect to y? Anybody want to try that one?
0.
0. Why? WHY.
It's a constant.
Because I'm treating it as a constant. Exactly. But sine x is a function. Not in terms of y, it isn't. Oh, and right now when I differentiate with respect to y, everything that is not a y is a constant. But wait a minute, what about over here? These are being multiplied. So the other term is like a coefficient. This is a standalone. There's no y's in that term, so I treat it as a constant. So its derivative is in fact 0. So then the last one would be minus 3 sine xy. But the derivative of xy with respect to y, now x is the coefficient. So I'd say times x. And again, I'd probably move the x in front because it reads better. Oh boy, so that was interesting. You didn't see that coming, that the derivative of the function would be 0 because I differentiated with respect to a different variable. Okay. So let's keep going. Now I wanted to show you something else. Again, keep it really simple. Let's go back to the first problem that we did now that we know how to do it really quickly. So z equaled 4x squared y cubed. The partial of z with respect to x. Okay, what was that? We said that was 8xy cubed. The partial of z with respect to y was 12x squared y squared. Well, it turns out if I have a function of two variables, there are 3 second derivatives, or you could even argue there are 4. Really? 4? Yeah, I've got the second order partial with respect to x. I've got the second order partial with respect to y. I have the partial x, y, and I have the partial y, x. Usually we think about it, we're doing the inside one first, because remember how functions work? Like if you have a composition of functions, f of g of h, h is the first one evaluated. You work your way out. So this would mean I'm differentiating with respect to y and then taking the result. This says, whoops, sorry, this would be x. I'm differentiating with respect to x and then I take the result. So let's see if we can figure out all these guys. That means for this one, I am looking at this one and differentiating with respect to x. So what would that be? Just yell it out if you think you know. With respect to x, what would that be? Anybody?
8y to the third.
8y to the third. Beautiful. Okay. This one with respect to y.
24x squared y.
24x squared y. Now the next ones are a little trickier. This says I already had the y derivative. And now I'm going to differentiate the result with respect to x. So what's this derivative with respect to x? With respect to x.
24xy squared.
Now, drum roll. I've already got the derivative with respect to x. Now I want to differentiate this one with respect to y. So what would that be?
24xy squared.
What a coincidence. They ended up being the same. Or is that supposed to happen? Turns out that's supposed to happen. Now I'll give you this simple. I have a function of two variables. I'm going to fix the x and differentiate with respect to y. Then I'm going to fix the y and differentiate with respect to x. That means I'm making one a constant when I differentiate with respect to the other. So that means the one that I'm holding constant isn't affected. It's not being changed. So the order that I differentiate cannot affect the answer. These are called cross partials. This is called the second order partial, the second order partial, the second order cross partials, because I'm doing across two different variables. The second order cross partials, or cross partials in general, are always equal. Now, when I was in school, it was really funny. They'd say that these aren't necessarily equal. They're equal as long as if I take an open, in this case, an open circle on the XY plane, an open region around the point in question, as long as I'm continuous in that open region, then those will be equal. And I remember asking, like in an upper division class, can you give me an example of something where those are not the same? Can you give me a function or a situation where those would not be the same? And the smartest person I ever met said, no, I can't give you because the example where it fails only exists in theory. Out of the infinitely many functions that exist, none of them ever fails the cross partials of being equal. But in theory, it's possible you could design something that failed like at one point in the whole, no. So in other words, the cross partials are always the same, period. Now, do you ever have to take them both? No. Should you always take them both? Yes. You always take them both. Here's why. If I take this one, I get this answer, and I take this one and get this answer, that means that I now know both of these were right. So by taking the cross partials independent, in other words, I went x first and then y, or I went y first and then x, I have to get to the same place. And if I get the same answer doing two alternate routes, I can be pretty sure that all my derivatives are correct. But what if either one of these was in error? I made a mistake. If either one of these are in error, then my calculations here would have been different. And then I know I have a mistake somewhere. I can go back and, well, hopefully I can find the mistake and fix it. So this is one of those situations where you never have to do them both, but you always should from the standpoint of checking, okay? Because it's really the only way to check. Remember, when you integrate something, you can check your answer through differentiation. But when you take a derivative of something, you really can't check your answer. That's like in baby algebra. If I said, here's a polynomial, I want you to factor it. So you give me a factored answer. Your check is multiply back out again. Great. But if I give you a couple of binomials and I say multiply them out, you did. How do you know you did it right? You see, the check only goes in one direction. So generally, when you don't have any way of checking if that's right. You don't have any way of checking if that's right. But if these are the same, there's no way either one of these could have been wrong because you did them independent. So let's do another exercise here. Okay, this one is going to be for everybody. And I will even pause the recording in a moment so we get some practice. All right. F of xy equals 6x squared times the sine of y minus 4y cubed e to the x. I want you to find fxx, fyy, fxy, which we know is the same as fyx. I want you to find all the second order partials. Now I'll give you a hint. You can't find the second derivative unless you do what? Anybody? We're going to tackle that one. Cannot find the second derivatives until what?
Get the first.
So there's kind of an order of things here. So I'm going to give you a couple minutes. I want everyone to do this on their own for a moment. So I'm going to pause. Now that we're starting to finish, let's go ahead and walk through. I see a product but it's not a product of functions in the same variable. So one of these is going to be a constant as I go through. So the partial with respect to x means I hold sine y fixed. It could be the number 3 for all I care. It's just multiplied as a constant. So the derivative of the 6x squared is 12x. So that first derivative is 12x times the sine of y. Okay, over here, 4y cubed is treated as a constant. So I'm really just differentiating the e to the x, which is just e to the x. Oh, now you know that integration is coming someday, okay? And so integration obviously would be the same thing in reverse. So when we get to the integration, it's going to be the same thing. You integrate one variable at a time, holding all other variables fixed for the same reason. So now I'm differentiating with respect to y, so 6x squared is treated as a constant, and the derivative of the sine is just the cosine function. So this will be 6x squared times the cosine. Over here, e to the x is treated as a constant, so I'm just differentiating negative 4y cubed, and that'll be negative 12y squared, and then e to the x. So hopefully you found that part right there very, very simple. Now, this is the second order partial with respect to x, which means I'm differentiating this answer right here with respect to x. And it's important I realize that which one I'm actually doing. So here, the derivative of 12x is just 12, and then times the sine of y. The derivative of e to the x is still just e to the x times negative 4y cubed. Okay. Here, I'm differentiating this part with respect to y. So I'm differentiating the cosine, which will be negative the sine. So this will be negative 6x squared sine y. I'm differentiating this, which would be negative 24y, then times e to the x. Now, the last part, it's not meant to be confusing or tricky. Usually we read it, like I said, inside out. So x derivative first, then y. So this means I'm taking the derivative of this one here with respect to y. I'm differentiating this with respect to y. So the derivative of the sine function will be the cosine. So that will be 12x cos y. Here, I'm going to have a negative 12x squared. I'm sorry, negative 12y squared, not x squared, e to the x. Okay, now completely ignore that. The last one says I'm taking the derivative with respect to y, and I'm going to differentiate this with respect to x. So with respect to x, that would give me 12x cos y. With respect to x, that'll give me negative 12y squared e to the x. Is this a good thing? This is a great thing. Because these are the same, gives me confidence that these two are correct. By the way, I still could have messed these two up, but I have utter confidence that these two are correct, because otherwise, if either one of these were incorrect, this would be an impossibility. Okay, so part of the reason you actually probably want to do it from both directions is then that just ensures that you did it right. When we found tangential and normal components of acceleration, I said you can use the Pythagorean identity to get the other one, but that's dangerous because if the first one's wrong, then they're both wrong. If you find them independently, use the Pythagorean identity, I said, to check your answer. And that's a way better way to go, because then when it checks, then you know they're both right. Right? You then you found them independent of each other. So this is how you take a partial derivative. What's it used for? Well, basically everything. This is the way differentiation actually is. Now, what we're going to see is over time that when we're working with multiple variables, the rules don't change as much as they expand. I can do more things. All right. Now, what is the most hated form of differentiation in Calc 1? Anybody remember? What kind of, we just did it last week in my Calc 1. What's the worst? Anybody remember? When I tell you, you're going to go, oh yeah. No. What kind?
Fractions, when the variables are stacked on top of each other, it's kind of.
Maybe, but that's probably extra power. How about implicit differentiation? Oh, remember that? That's when you had x's and y's mixed together and you had to treat y's as functions of x and then do it and then gather. Most people say, yeah, implicit is the most evil thing ever invented. It was invented by the guy who was always picked last for kickball. You know that guy? You guys remember him in elementary school? Yeah. He was the guy that invented implicit differentiation, I'm pretty sure. Okay. And in Calc 1, it's just brutal. My Calc 1 folks just turned in their first quiz today and they did okay, but man, it's confusing because it's what you do when you don't have a function. It's how you differentiate. Well, we're going to do implicit differentiation in multiple variables next day. And you're going to absolutely love it. You're going to go back to Calc 1 and say, oh my goodness, those problems are so much easier now. You say, how could they be easier? Because remember what I said last day, anything you can possibly imagine in 2 dimensions is nothing more than a slice of something in 3. And if implicit differentiation is only used when I do not have an actual explicitly defined function, I cannot isolate the y or f of x. I can't write it as f of x equals, like a circle. I have to do it implicitly because it's impossible to isolate an independent variable. But if I think of that as being a slice of something in 3D, and then I think about it in these terms, I'm going to show you that implicit differentiation is just the same as anything else. It's not harder. Not in any way is it going to be harder, but I have to look at it as a 3-dimensional problem. That 2-dimensional question I was asked, I have to look at it as a slice of a 3-dimensional problem, a level curve. And once I do that, then I can actually do implicit with even more variables, 3, 4, 5, 10 variables, and it will be the same rules. It's really cool because when I go into higher dimensions, again, it's not that the rules all change, it's things expand. I can do things I couldn't do before. And that's very, very comforting. Now, what if I have even more variables? Well, the notation is still the same. You know, I could have a function of x, y, and z. Well, then I do partials with respect to x, y, and z. So I'm going to do a simple application. All right. We say that f of x is harmonic if the following is true. By the way, I do not need you to know anything about harmonic functions. This is just an exercise in taking partial derivatives. That's all it is. But a harmonic function, it turns out later on when you get to physics and when you get to differential equations and things, harmonic functions are kind of cool. That's all, you know, they're just kind of cool things. There's nothing about it that I need to know in Calc 3. But what I want to do is give you a function, and then I want you to simply see if that's a true statement or not. So in general, if I gave you just an arbitrary function of x and y, do you suppose that would be true in general? No, it's pretty much never going to be true. It would have to be a very special function indeed for that to be true. Now, the term harmonic, that's one of those horrible math terms that depending on the context, it means something completely different. For example, the harmonic series, remember what that was in Calc 2? That was the sum of 1 over n. So it's 1 plus a half plus a third plus a fourth plus a fifth forever, never, never, never. This is a harmonic function. And then in differential equations in physics, you'll study something called harmonic motion that has absolutely nothing to do with those things. Harmonic motion would be like a shock absorber, right? Like a sine wave that's getting smaller. That's harmonic motion. That's not a harmonic function, and that's not the harmonic series. Those are 3 important harmonics that we study in math that have nothing to do with each other. And again, I don't know why we keep using the same word. It's like we couldn't think of anything better. So let's consider that f of x, y is the, let's see, which one do I want to do? Hold on. I've got a couple. Is the natural log of the square root of x squared plus y squared. Now, again, there's nothing special about this function. This is just an exercise. So what we want to do is take 2 derivatives, one with respect to x and the other with respect to y, not the cross partial. I'm not interested in the cross partial in this case. So how do I do that? Well, one of the things I remember about logs, this is one of those really important log rules. Remember, log of anything raised to a power. Remember this? Always makes that crazy crashing sound. That's always true. Well, this technically is 1/2 power. I would suggest doing this as my very first step of the problem before I do any calculus, because differentiating this would be a little bit more work, because I'm going to have to take the square root of a function and then differentiate that. That can be kind of messy. It'd be much easier if I do this first. You don't have to do this. But this will eliminate more than 50% of all the steps, including all the steps I'm most likely to make mistakes on. So that's why I'm doing it. Now, what is fx? Well, remember, how do you differentiate a logarithm? So it'd be, keep it simple. Remember, the derivative of a log is 1 over the argument times the derivative of the argument. So I'll write it like this. What's going here? Well, my chain rule factor in this case would be this. Okay. Again, the rules of derivatives for a particular function haven't changed. And my chain rule doesn't change. It's just I'm differentiating everything with respect to x. Well, what is this? That's just 2x. Okay. So now that gives me 1/2 times 2x over x squared plus y squared, which is simply x over x squared plus y squared. Oh, that was easy enough. Now, what's the partial with respect to y? Well, 1/2, 1 over x squared plus y squared times the derivative with respect to y of x squared plus y squared, which is 1/2 times 2y over x squared plus y squared, or y over x squared plus y squared. Oh, I probably should have seen that one coming. Right? They have the exact same form. It seems reasonable. All right. Now we have our first order partials. So I'm going to put those up top. So I need the room now. So fx, what was it? It's x over. Fy is y over. Now let's do the second order partials. Okay. Well, in order to do the second order partial, I need to differentiate this guy with respect to x. So let me put him up here. Now, in this case, I actually do have to use quotient rule because I can't simplify that, and my denominator is not being raised to a power. This is just straight up quotient rule, nothing clever. Okay, so quotient rule is bottom times derivative of the top with respect to x minus the top times the derivative of the bottom with respect to x. That would simply be 2x over the square of the denominator. Now see if we can clean this up. That's x squared plus y squared minus 2x squared. So that'd be negative x squared plus y squared over x squared plus y squared squared. And I cannot simplify that because it's the square of a sum of squares on the bottom, but it's a difference of squares on top. So that's as far as I can go. If I could reduce that, I would, but I cannot correctly reduce that. All right, let's, I'm going to erase this. I don't want to squish this in too much. Okay, so now I'm taking this result. So I've got the bottom. Now I'm differentiating with respect to y. So derivative of the top again would be 1 minus the top times the derivative of the bottom, but the derivative of the bottom with respect to y is 2y over the square of the bottom. So let's see, that's x squared plus y squared minus 2y squared. So that'd be x squared minus y squared. Okay, I guess I don't really need it on top. In fact, let me go ahead and finish here. So, question was, is this thing harmonic? Well, how do I decide if I add up the squares? Oops, my timepieces failed me here. There we go. If I add up the squares, I'm sorry, not the square, the second order partial, sorry. Then I'm going to get negative x squared plus y squared over this plus x squared minus y squared over this, which I do believe is 0. Right? Crowd goes wild, confetti everywhere, dancing in the streets, the whole 9 yards. Okay, so what is our conclusion? Yes, F is harmonic. That's it. Okay, nothing else. We're not going to use it to answer any questions. We just wanted to do some analysis. Basically, just take some derivatives and check them out. Okay, now I am going to stop in terms of the lecture, but I want to now talk about the exam a little bit before we go into office hours. So we have an exam on Thursday, as you know, and the exam basically covers everything vector-ish that we did. And so the nature of the exam is what I want to go over, and all the rules and everything else, because face it, some of you haven't done an exam on Zoom or an exam this way in this environment. And it's, it can be a little bit stressful, it can be a little bit taxing. So first and foremost, the exam is the class. If we were on campus, we would be taking the exam during the regular class time. And so we're going to do the exam during the regular class time on Zoom. So you're going to log on, right? And by the way, I'm going to send out some emails, but you're going to log on probably at least 10 minutes early. But I'm going to email you the exam about 10 minutes early or so. If you have a printer, print the exam, then you don't have to worry about it. That makes it easier. If you don't have a printer, one of two things: either you have to quickly write down the questions, or you have to have some sort of split screen. As long as the camera's on you, I don't care if you have that split screen. But again, it makes it hard, because that means your eyes are going to be, staring at a screen for 2 hours, or that can be a little bit difficult. So you're going to take the exam with the camera on you. Now, this one always makes me laugh. I did this last semester, and so as soon as people would log on, every person would then do this right after they logged on. Let me see if I can get it. So I'd have a class of people, and this is what I'm looking at. Well, the moment they did that, I suspected they were cheating, and usually they were. And whoops, uh-oh. Hang on a minute. I just lost my picture. Hold on. There we go. Oh, that was scary. It just disappeared for a minute. No, you're not going to. I need to actually see you physically working. I've had students, they can't help themselves. They have this separate screen right next to it, and they doing this. Well, no. You're going to take the exam. When you're done with the exam, you're hopefully, finally, some of you will get this right. You're going to use the Fast Scanner app. Don't even bother sending me the exam in any other format. Half the time, I can't even open it up. You take the pictures with your cell phone. Picture, 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 send. That should take a maximum of 30 seconds. And you take all the pictures and send one PDF. Don't send me 10 PDFs, send me one. Fast Scanner can handle 10 different documents. Picture, 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 send. That's it. Now, here's one of the things I have to keep asking people and reminding people: set the contrast on the Fast Scanner to the darkest level. A lot of people aren't paying attention to that. So you're taking a picture of something that is this clear, but it's coming out more like this white. A lot of times you don't realize how light something is when it's coming through. So set the contrast a little darker, certainly below the middle. And the Fast Scanner has the ability to set the contrast. Please, a few things. Take all of the pages in the same orientation. Because you're sending them as one PDF, it's really hard to rotate only part of it. Okay, so take all the pages, preferably put the pages in order. That makes it easier. But since it's one PDF, scrolling isn't as hard. When you're sending them as separate PDFs, one of two things: it takes forever to go through, because it takes a while to open each one. And if they're not in order, it's even worse trying to find the one. So make my life easier by that. You may use a cheap scientific calculator. That means, by the way, the term scientific calculator means there's absolutely no calculus functions on there. You don't have a lot of derivatives, but you got a little bit of derivatives, because you're finding, the derivative of some R of t, not exactly complicated. But you don't actually need a calculator at all, except you have to do a little bit of arithmetic. And I would really rather you not do arithmetic, pencil and paper. You have this perfectly flawless calculus answer, and then the wrong numerical result because you multiplied two numbers badly. You have the calculator for the little arithmetic stuff. Now, the exam is going to be basically a lot like the practice test in terms of things are being grouped. So in one section, like on the practice test, I'm going to give you a couple of vectors in R3 and say, what's the dot product? What's the cross product? What's the projection? What's the angle between them? How far is this one from that vector? That, absolutely straightforward, exactly like this. I'll have another section where I'm going to give you maybe 3 points in space and say, find the equation of the plane that passes through those 3 points. Tell me the equation of the normal line. Now, here's a point in space. Find the equation of a line that's going through that point. Here's a point in space. How far is it from that plane? These are all things, what is the area of the triangle or the parallelogram uniquely determined by those 3 points? These are all questions we've done multiple times. All of the questions of this nature will be grouped. Okay, so you won't be having them random all over the place. I'm going to give you some really simple surfaces and say identify the surface. I'm not going to ask for cross sections. It's up to you to figure out that, hey, I need to come up with cross sections. If it's cylindrical in nature, how do you know it's cylindrical? Anybody want to try that one? If I say find the surface, how do you know when it's cylindrical? There's only one way to know that.
If it's a conic section.
Well, careful. Y equal x squared is a parabola.
Mhm.
In 3 dimensions, y equal x squared is a parabolic cylinder. In 2 dimensions, it's a parabola. So how do you know when it's a cylindrical surface?
I don't know.
Anybody? Peace. No. How do you know when it's a cylindrical surface? There's only one way to know. 2 what?
2 variables.
Is it? There's no other rule. That's it. If you're in 3D, but you have only 2 variables, it's cylindrical because that means one of the variables is the same forever. So like the circular cylinder, that's an easy one for people to think, oh, I see the equation of a circle, but because it's 3-dimensional, it's a cylindrical, right? It's a circular cylinder in that case. So it's a cylindrical shape because there's 2 variables and you were asked for a surface. So now the conics. I'm not going to give you anything higher than 2nd degree. Don't worry, that you're not going to see anything you haven't seen before. So now you got 3 variables. Now you look at the cross sections. Okay, this one's a parabola, that one's a parabola, that one's a hyperbola, hyperbolic parabola. Remember the one that has more wins and gets the oid. That's how you always remember. Okay, so that's not something that should challenge you. I'm going to give you a motion problem. Really, really simple. Throw a ball up in the air with an initial speed. So the same things, model the movement. And by the way, we are doing this in a vacuum. So like I said before, so we're not worried about air resistance and things like that. And I'm going to give you it in feet and seconds just because then you can use 32 rather than 9.8. And the funny thing is a lot of people don't even realize it's not 9.8. If you were in a physics class and you use 9.8, I know at Mesa College, you get it marked completely wrong. What are you required to use at Mesa College? Anybody know?
9.81 meters per second.
Yeah, you
squared.
better use 9.81. And by the way, it's not 32. It's actually 32.18 approximately. We use 32 because it's happy and round. We use 9.8. 9.8 is neither happy nor round. It's no, I'm not going to give you any. I'm not worried about the decimal. No, so we're going to use 32 because it just makes it easier to do the math. Remember, it's already artificial. We already have no air resistance. And of course, all of us play catch in a vacuum on a regular basis with our spacesuits on. Now, most of you did a fantastic job on that kind of stuff. That's not really the issue. Let me see what else we got here. Oh, and of course, probably the biggest ticket item of all. I'm going to give you an R of t. I'm going to give you a vector that is describing motion, right, at any particular time. And I'm going to ask for everything. I'm going to ask for V and A and capital T and capital N and curvature and tangential and normal components. But I will ask all of these things at a particular time for the really simple reason. As the further you go, particularly things like the curvature, the tangential and normal components, those are really difficult to state if they're still in functional form. Plus, it's not very realistic. You don't say, what's the curve? I have some windy road. What's the curvature of the road forever? No, you say, what's the curvature of the road at that point? Oh, okay. So I will ask you, find all of these things at t equal 2. So you find, V of t, and then tell me what's V of 2. Find A of t, then tell me what's A of 2. Find t of t, then tell me what's t of 2. N of t, then tell me what's n of 2. Because then your k, your at, and your an will automatically be constants. Then if you're going to do the dot product, right, it's your V of constant dotted with A of constant. A lot of you on the quizzes, you are not lazy people. Oh my God, you're making things hard. Remember, once you've taken your last derivative, which generally is going to be the A, once you've taken your last derivative, that's when you can evaluate. So a lot of you are doing your A dot T, excuse me, your V dot A and your V cross A, and you're doing them correctly. but you're doing them while they're still in function form, getting some big hideous answer, and then you're evaluating that. No, 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 no. Do V and A evaluated. Now they're really simple, tiny vectors, and then you do the dot and the cross product because you're already done with derivatives. The only reason you have to wait till you're done with derivatives is if you evaluate V and then you take the derivative, you're going to get a zero vector. So that's something we already know. But when you're doing and we call that the backdoor method. Okay. So let's see. That's pretty much everything. Yeah. I'll also give you some motion and ask you to write it in terms of the tangential and normal. And again, most of you did a really good job. And like every exam, I will throw a bonus question on there, an extra credit. And I throw an extra credit for one really simple reason. If you were writing an English paper for 2 hours and you don't get to use the spell check, you got to do it by hand. Is there anybody who could write for 2 hours and not make a single misspelled word, a single punctuation error, a single run-on sentence? No, nobody can do that. That's why we proof them later on. Well, if you're writing math for 2 hours, there's going to be a lot of math typos. In fact, worse, there's going to be a problem, usually almost every single person, a problem that you're the resident expert on. You were tutoring people an hour before the test. And then when you looked at that question, you saw something completely different. And you completely tanked a question that you know inside and out. And we've all done that. I throw an extra credit question as a buyback for that problem right there, because almost everybody has one of those. I can't tell you which one it's going to be because it's going to be different for every person, but people will miss something they know well. To me, if you know this at an A level and you write a B test, that is not a good test. If you know this at a B level and you write a B test, that's a fantastic test because you were able to show everything you knew. Okay, so part of this is good proofreading. Most of us aren't great proofreaders, myself included. The only difference really between a 95 and a 100% exam is the 100% exam caught all their small errors, the 95 didn't. Doesn't really show any difference in skill, just in proofreading. So I'm going to throw an extra credit on there. Most of you will finish. You have 2 hours. Most of you will finish significantly shorter than 2 hours, just because there's no problems that are really that long or that difficult. But it's 2 hours because that's class time. There is no lecture. It's just the test. When you're done, you turn it in and then you go on your way. It's important that I'm able to read these things. Now, what can you bring? Okay, this is very important. No test is going to be open book, open node. Heck, might as well just have your tutor there with you when you're, if that's the case. Any theorem, formula, or definition that we have derived or created in this class, you may write down. You can use a 3x5 card. And by the way, you couldn't even fill one side of a 3x5 card. We don't have that much stuff yet. But both sides of a 3x5 card, and you're going to be showing that to me before you start the test. So I'm talking about things like, if you're not familiar, let's say you've never had physics and vectors are brand new to you. Okay, you might want to write down just simply the definition of dot product being the sum of these products. I'm pretty sure you all know that, but writing down the angle between two vectors, writing down the projection of one vector onto another, because that's not stuff that a lot of you knew ahead of time. Write down the formula for distance from a point to a plane or a point to a line. Ooh, yeah. See, these are the kinds of things that you're probably great at, but you only learn them this semester, and you may or may not have them right there in front of you at the top of your head. So I strongly encourage people. Now, what can't you write? Well, you can't write derivative and integral formulas from Calc 1 and 2. That's incoming knowledge. People write, well, can I write all of my trig identities? No, you can't actually write any trig identities. Why? Because you're supposed to know that entering pre-calculus. Forget Calc 3. No, nothing you were already supposed to know, derivatives, integrals, trig identities, but certainly vector facts. If there's terminology, if there's vocab that we have used that you are unfamiliar with, you could write down the definition of a word. That's not a problem. I just talked about surfaces. Ooh, so if it's a surface and there's two variables, that's cylindrical in nature. That's the definition of a cylindrical shape. You could write that down. Cylindrical shape is three-dimensional surface with only two variables. That might be wise, because then when you get to it, you're less likely to mess it up. So you do not have to, but I strongly encourage you to write down theorems, formulas, definitions. Now, those have been in my class before. You know how many times you're actually going to look at the formula card. Usually the universal average is this many. You never actually look at it. Then everyone says, well, then why did I bother making it? That's why you made it. In the making of the formula card, you reinforce all of the things that you deemed important. And then when you get to the test, you never end up having to look at it, or you glance, is it a plus or a minus, you know? Most people say they never even look at it because you made it. It's the creation of the formula card, not the existence of the formula card, that's important. In your creation of it, your organized thoughts of how you're going to put everything down, you end up, that's so much extra review for the test that it's unusual if you have to look at it. And then the flip side is if you have to stare at that card for a length of time, then you probably don't know how to do the problem, because having a formula isn't going to get you through a problem. You have to still know which formula to use and how to correctly use it. I just don't want you to worry about memorizing minutia. Okay, you already are showing me how to think in the process of answering questions correctly. If you are a DSPS person and you're here today, I do want to talk to you because the whole formula card thing is going to be an issue, and there's still some paperwork. So make sure that you don't leave with unanswered questions. Let's see. That's most of it right there. Anyway, I'm going to go ahead and stop now.